Welcome back. We've been talking so far about continuity, and frequently I've been making reference to the reason why a limit not existing is because the graph is doing different things on the left and on the right. So it would be very useful if we had a way of talking about specifically what's happening on the left, what's happening on the right, and doing that sort of separately. Because up till now we've been talking about limits, and when we say limit x approaches c, that's approaching c from both sides. So we might want to just say, well, a left-handed limit, what happens if we approach that c value from the left, approaching from values that are slightly smaller than c? So the notation that we have there is approaching c from the left, we put a little superscript of a minus. So this doesn't mean that the number is negative. It just means we're approaching that number from slightly smaller values. So for example, if we were approaching x approaching 0 from the left, we'd be talking about things like negative 0.00001 or negative 0.00000003, things that are small, close to 0, but on the left side of it. And if we're talking about limit x goes to 0 from the right-handed limit with the plus, those would be using values slightly larger than 0, like positive 0.000001. And of course, it doesn't have to be 0. It could be any number where we're looking at it from the left and from the right. So if we were looking at the limit as x goes to 1 from the left, that would be numbers slightly smaller than 1, like 0.999, things like that. Limit as x approaches 1 from the right would be using numbers slightly larger than 1, like 1.01 and things like that. So if we have the limit approaching c from the left exists and it's some finite number L, then we would write that. Left-handed limit is L. If it approaches some finite number on the right side of c, then we write the limit on the right. The right-handed limit of f of x is L. So now we've got this little graph here, and we want to talk about what's the limit, if the limit exists at all. And so even though the function itself might not have a limit existing, maybe the left-handed limit or the right-handed limit exists. So starting with the first one, f of x, we want to look at the limit as x goes to 1 from the left. So here's 1, and what's happening is we're approaching 1 from the left, so from values slightly smaller than 1. Our y values are actually all 2, so as we're approaching 1 from the left, the limit is 2. But on the other hand, as we're approaching 1 from the right, so here's 1, and approaching it from the right, as we're making our way close to 1 from the right side of things, the y values are getting closer and closer to 1. And if you ask me just overall, what about the limit as x approaches 1, I would say, well, the limit doesn't exist. We're not approaching the same thing on the left and the right-hand side. And you can see now why. We can say formally that limit doesn't exist because on the left side we approach 2, and on the right side we approach 1. The left and right-hand limits aren't the same. We can see, though, for 3 that if you're looking at the limit as what happens as we approach 3 from the left, the y values are all getting close to -1. And as you approach 3 from the right, the y values are also getting close to -1. And so since we're approaching -1 from the left and also from the right, then I can say just in general, my limit as x approaches 3 for f of x is -1. Okay, a nice little function. This is one that is used in a bunch of little counterexamples throughout calculus. The greatest integer function, because it's a nice example of a function that has lots of discontinuities and places where it's constant, and it's got some interesting properties. And this is the function that basically what it does is it rounds things down. That's why it's called the greatest integer function. If you give it a number in, it's going to give you the biggest integer, which is less than or equal to whatever you gave it. So if you gave it an integer already, then it will just give you that integer back. So if you give it a 4, it'll spit out a 4. But if you give it a number that's not an integer, it's going to round it down to the nearest integer. So 0.3, rounding it down to the nearest integer, is 0. Negative 1.1, rounding it down to the nearest integer, is negative 2. If you're having trouble seeing that, of course, easy enough to draw yourself a little bit of a number line, and it makes it a little bit more obvious when you're looking at the rounding down. Negative 1.1 would be over here, so the biggest integer that's below it would be negative 2. That's why the greatest integer function for negative 1.1 rounds down to negative 2, whereas something like 0.3 rounds down to 0. Other books will call it, instead of the greatest integer function, they'll call it the floor function, and they'll use a slightly different notation. You'll see that sometimes in discrete mathematics or in computer science. You'll also see a related function, the ceiling function, that does the opposite. It rounds things up. So a ceiling of 3.2 would be 4. Our textbook that we're using uses the greatest integer function written this way. So when we see this symbol in our text, we'll know that that's greatest integer function, and that is rounding things down to the nearest integer. So for this, if we're looking at the limits, if they exist for this function, we want to look at the limits as we're approaching 1 from the left, from the right, from both sides. What happens as we approach 1.5 from the left, from the right, from both sides? So for this one, we can do this with drawing a graph. That might be a little bit helpful for you. So if we're thinking about drawing a little bit of a sketch of what does this function look like, we have to remember that whatever it does is going to take our x values and then round them down to the nearest integer. So I'm just going to draw my x values. There we go. I'm not going to draw the full graph of it. I'm not going to draw much of the graph either. But let's say that if you're talking about values that are 1, if I gave you a y value, x value of 1, that's already an integer. Your y value would be 1. If I gave you something a little bit bigger than 1, 1.2, 1.3, even all the way up to 1.99999, all of those numbers, when you round them down, they would round down to 1. If I gave you something a little bit smaller than 1, like 0.9 or 0.8 or 0.7, all of those numbers would round down to 0. So you can see what we're kind of getting here is a function that's going to look like a little bit of a stair-step function. When x is 2, the y value would be 2, and when people are a little bit bigger than 2, they will round down to 2. So we have a function that will sort of have that kind of a look to it. So now if you're talking about x approaching 1, if you're approaching 1 from the left, the y values are approaching 0. If you're approaching 1 from the right, the y values are approaching 1. And so what's happening is we're approaching 1 on the left and right side, different things, so therefore the limit does not exist. But 1.5, whether you're approaching it from the left or whether you're approaching it from the right, the y values are approaching 1 on both sides. So the limit as x approaches 1.5 on both sides is 1. And that sort of brings us to this important theorem, which we've kind of been using in a sense, or I've been dancing around it a little bit here with our last couple of examples, the connection between the limit existing and the left and right-handed limits existing. So if you have a function and you have the limit exists, then you can conclude that the left-handed limit exists and the right-handed limit exists, and they are the same as each other and the same as the limit itself. But the reverse is also true. If you have the left and right-handed limits both existing, if they're both equal to each other, then the limit itself exists and is the same thing as the left and right-handed limits. So if you know that the limit exists, then you know that the left and right-handed limits both must exist. And if you know that the left and right-handed limits exist and agree with each other, then the limit itself exists. So you've got this function, g of x, and I've given us left-handed limit at 3, right-handed limit at 3, left-handed limit at 4, right-handed at 4, and just limit in general at 5. So if I were looking at the limit as x goes to 3, I would say, well, that would exist provided that the left and right-handed limits exist and provided they agree with each other. So my left-handed limit at 3 is 5. My right-handed limit at 3 is 5. The limit exists on both sides of 3, and the limit is the same on both sides. So therefore, my limit as x goes to 3 must be the same as those left and right-handed limits. They must both be 5. 4, on the other hand, I would say my limit for 4 does not exist. And that's because for 4, on the left side, we're approaching 2. On the right side, we're approaching 3, so we're approaching two different numbers on the left and on the right. I would say my limit as x goes to 4 does not exist. And as far as the last part of it goes, if I know that the limit exists as x goes to 5, then I know that the left-handed limit and the right-handed limit must both exist, and they must both be the same. And so in other words, if the limit as x goes to 5 is 6, then as x goes to 5 from the right should also be 6. And now that we've talked about functions being continuous on an open interval, we also need to talk about them being continuous on a closed interval. So for example, if you're thinking about the function y equals square root of 1 minus x squared, so this would be the top half of a unit circle. I know for that function, its domain should be all the values between -1 and 1. And for sure, we can talk about it being continuous on the open interval from -1 to 1. We can definitely do that, and it wouldn't be too hard for us to show that. However, we also want to be able to say something about the endpoints, that basically between the first point on the far left at -1 and the endpoint at the far right, that it's one nice smooth curve. Of course, for continuous everywhere on the inside, we were looking for limits to exist, which meant we were looking at approaching the points from the right and also from the left. But if you're thinking about my two endpoints, at -1, I can only really approach that from the right, and +1, I can really only approach that from the left. So here's where we use our left and right-handed limits to talk about being continuous at those endpoints. At -1, I'm only approachable from the right. So when I'm talking about being approachable from the right only, then when I talk about continuity, I'd be talking about right continuity. And for that, I'd need to have what I'm approaching as we get to my endpoint from the right is what my y value is doing. And we see that that's happening on my graph here. As I approach -1 from the right, the y value is approaching 0, and the y value on my graph at -1 is indeed 0. Same thing for the point when x is equal to 1. For that one, I can only approach it from the right side of things, or from the left side of things, which means I can only approach it using a left-handed limit. And for it to be continuous at that far right endpoint, I'd be looking at it being left continuous, because I'd be approaching that endpoint from the left-hand side, and that what I get when I approach from the left-hand side is that y value at that endpoint. So for that endpoint at 1, I approach it from the left, and its y value is approaching 0. At x is equal to 1, the y value is exactly 0, so we are continuous from the left, or left continuous at that endpoint, because what I approach from the left is exactly what's happening at that y value. So you can also now do a similar sort of definition about being continuous on half open intervals. So something like the square rooting function, whose domain has one endpoint, 0, that it's including, but the other end is unbounded. So now you can talk about the square root function, for example, being continuous on that interval. So to be continuous on the closed interval, you just need to be continuous on the interior and then continuous at the two endpoints. If you wanted to be continuous on some sort of half open interval, you'd need to be continuous in the interior, and you'd also need to be continuous at the endpoint, the one that's being included.